January 1910. Halley's Comet is about to return. And this time, say scientists, the Earth will pass through its ghostly tail. With each passing week, this mysterious visitor becomes an ever bigger story. Comets have long been linked in people's minds to catastrophes of one kind or another. Plagues, wars, the death of kings. Even some scientists are concerned. A French astronomer, Henri Deslandres, warns of dramatic changes in weather. And indeed, just weeks before Halley's arrival, Paris is staggered by the worst flooding it has seen in decades. Deslandres' colleague, Camille Flammarion, has an even graver worry. He fears gases in the comet's tail might combine with nitrogen in the Earth's atmosphere to produce enough nitrous oxide, or laughing gas, to cause contagious gaiety, paroxysms of delight, and in the end, widespread madness and death. In 1910, comets are almost as mystifying as they were when 17th century British astronomer Edmund Halley realized that one in particular returns to the center of our solar system every 76 years. As Halley's namesake approaches, the excitement, anxiety, and business opportunities grow. But then, when it has come and gone, it is science, not superstition, that claims the day. Using newly developed tools, scientists gather photographic and spectrographic evidence that proves the comet's tail is too diffuse to affect our atmosphere, and that its icy heart is but a tiny fraction of the visible whole. As the 20th century dawns, there's a growing sense that the mysteries of our universe aren't as far beyond our grasp as we once believed. In my grandfather's time, at the turn of the century, the night sky is the greatest show around. It plays week after week, even on Sundays, assuming the weather holds. Part of its power is its infinite mystery. No one knows where stars come from or why they shine. Few believe we will ever understand what the universe is made of, what the true nature of matter really is. But then, within a few years, all hell breaks loose. There are revolutions in astronomy and physics, and long-cherished ideas are shattered about the nature of the universe, of space and time, and even reality itself. The only thing that remains the same is the glory of the view. From the moment the telescope is invented, it's our window on the universe. In the 18th and 19th centuries, ever larger and more elaborate telescopes reveal ever more stars. By the end of the 19th century, telescopes are so large and reveal so many stars, astronomers are working overtime just to catalog them. There seems little need to build even bigger instruments if all they can do is find more stars to catalog. But George Ellery Hale disagrees. He's passionately convinced a big enough telescope will change astronomy in ways it's impossible to anticipate. And he's determined to make that happen.
That passion brings him to Mount Wilson in Southern California, where the air is almost always free of turbulence and clouds. It's the perfect spot for an observatory. With funds from the likes of steel tycoon and philanthropist Andrew Carnegie, Hale sets out in 1908 to build on Mount Wilson the world's largest telescope. The instrument he envisions will be almost twice the size of any then in use. It will collect and focus light with a mirror 100 inches wide. Hale's enthusiasm is infectious and persuasive. It also masks the enormity of the technological challenge he's undertaking.
Nobody is pouring glass, molding glass at the size that it's going to be necessary. Nobody is creating the kinds of beams and girders and the superstructure that's going to be necessary. These things weigh hundreds of tons, thousands of tons. You also have the difficulty that they're located on mountaintops. You have to build the roads. You have to build the living quarters for the astronomers. You have to have machine shops on site. It just goes on and on and on. These are almost kind of technological kingdoms in their own right, and they've never been designed on this scale before.
Things seem to go wrong from the start. The mirror has to be the largest solid piece of glass ever made. A French glassmaker pours enough green glass for 10,000 champagne bottles into a huge mold and then packs the whole thing in manure to slowly cool it. Unfortunately, it comes out flawed. Twice more they try, and each time the giant discs crack as they cool. Lacking the money to try again, Hale orders his opticians to grind the first, in the hope its flaws aren't fatal. It takes 4 years of grinding and polishing to finish the mirror, and even longer to build the rest of the telescope and its dome. Hundreds of tons of steel and concrete are hauled up the mountain road at a cautious 10 miles per hour. Even at that speed, accidents happen. The steel sections of the telescope itself are built at an East Coast shipyard. Some are so big they must be shipped by boat to California. World War I has broken out, and German submarines are a constant threat. Long prone to bouts of depression, Hale's worries about the project begin to affect his health.
Later on, he admitted that he had been visited by a companion, sort of described as a little green elf who might come to his bed or sit on his shoulder, perhaps to give him advice about how to run his life, how to raise money, who to talk to. It's hard to say. The elf perhaps helped him work out some of this stress.
Whatever it is that carries Hale through, on November 2nd, 1917, the 100-inch telescope is finished. Its 100 tons of iron and steel move with the precision of a fine watch. Its 9,000-pound mirror can detect a candle 5,000 miles away. What Hale has built is one of the marvels of the 20th century. It will reign for decades as the best telescope in the world and prove beyond doubt the worth of big telescopes. To spend a night here is the dream of astronomers the world over.
You would open the dome, a kind of rolling like thunder, and you were alone on the mountain with a telescope. It's just you and the universe, or you and God, so to speak.
You'd sit at the platform at the telescope, guiding, making very fine adjustments on this magnificent instrument with a little hand paddle, with your eye staring down onto the illuminated crosshairs, and work there 8, 10, 12 hours.
Oftentimes it was extremely cold. In winter they wore heavy coats, sometimes they wore bearskin or sheepskin coats. You could literally have your tears freeze to the eyepiece, and they wanted hot coffee, but Hale wouldn't allow it. He thought it was poisonous to the system.
Easy, 20 hours.
Coffee isn't all that Hale keeps off the mountaintop.
In the 1920s, I would not have been allowed to work up here. In fact, I wouldn't have been welcome even as a wife or a visitor of any of the scientists. Hale, in his days at Yerkes, had found that the wives of some of the astronomers became a distraction to their monastic scholarly studies, and so they were essentially banned from the mountaintop.
Ironically, without the contribution made by a woman, the first great discovery made with the 100-inch might not have been possible.
The closest a woman could get to the field was, at the time, at the Harvard College Observatory, where major data collecting projects were in progress. Women were hired on to help to analyze the data, to do all the menial tasks that were below the duties of the men.
Henrietta Leavitt is one of a dozen women who studied tens of thousands of photographic plates taken by men at distant observatories. Leavitt's task is to examine plates taken at different times and look for stars that vary in brightness. She notices a pattern in one class of stars, called Cepheids, and realizes the time it takes them to reach their maximum brightness can be used to determine how far away they are. It's a landmark discovery. Before Leavitt, astronomers couldn't calculate the distance to any but the closest stars.
What Henrietta Leavitt did was provide one of the first, and still to this day, one of the most fundamental yardsticks in the universe. It is the measure by which all distances are determined. Without that, we'd be clueless.
All the astronomers George Hale brings to Mount Wilson will, at some point in their careers, make use of Leavitt's celestial yardstick. But there's one for whom it will have special significance: Edwin Hubble. A star athlete in college, Hubble had won a Rhodes Scholarship and studied law at Oxford University in England. Upon returning home, however, he decides against becoming a lawyer and heads off to graduate school to take seriously a fascination with the stars that he has felt since childhood. When Hubble arrives at Mount Wilson in 1919, he's a smart but arrogant 29-year-old who has taken pains to adopt what he sees as the proper image of an astronomer.
What he tries to do is to create this portrait of himself as a kind of natural-born patrician. He tries to lose his Missouri roots because I think he's embarrassed about those things. He sees the English gentleman as being the prototype of what he wants to become. He wears English tweeds, he wears knickers, which have gone out of fashion except on the golf course. He smokes a pipe.
He spoke with an affected British accent. He had dueling scars, which were said to be self-inflicted when whispered among the staff.
He loves being separate and apart from his fellow human beings, and he plays that to the hilt.
In time, most of Hubble's personality quirks are overlooked because he's an excellent astronomer with a gift for asking the right questions. Hubble wants to unlock the secrets of the nebulae, faint, fuzzy smears of light that have puzzled astronomers for 1,000 years. Even with Hale's magnificent 100-inch, their true nature eludes him for 4 long years. Finally, in October of 1923, while photographing one of the spiral arms of the Great Nebula in Andromeda, Hubble catches a break
He took a 40-minute photographic plate and developed it the next day and looked at it and thought he saw what was then known as a nova. That was another hot topic. That is, what were novae, what were stars that brightened unexpectedly. So his curiosity piqued. He decided the next night, which was a better night, to take another exposure and took a deeper photographic plate.
This plate has what he believes are 3 novae. Yet an even greater surprise awaits him.
Well, when he got down to the mountain the next day and he began to compare the plates with those that had been taken earlier, he discovered that one of the 3 novae was not in fact a nova, but it was a Cepheid. And it's a eureka moment. He writes in capital letters on the slide itself, VAR, exclamation point, for variable star.
Hubble knows instantly, thanks to Henrietta Leavitt's discovery about Cepheids, that this star and the system it's a part of must be very far away, and the universe must be far larger than anyone had dreamed.
Yeah, it must have been a good moment for him. What he found was that the distance to M31, the Andromeda galaxy, one of, turns out, our nearest neighbors, is about 2 million light years. So people had been talking about the scale of our galaxy, 10,000, 20,000, 30,000, maybe 100,000 light years. What this meant was that M31 and all those other galaxies were not part of our system. They were themselves big systems equal to the Milky Way.
There are, in fact, billions of galaxies, each one containing hundreds of billions of stars. Hubble's discovery of the stunning size of the universe and the multitude of stars and star systems that can be found within it changes forever our picture of the cosmos. That discovery alone would have made Hubble one of the great astronomers of the century. But he continues to study distant galaxies and makes an even greater discovery. For 5 years, he gathers data on the movements of galaxies, recording where they're headed and how fast. If a galaxy is moving away, its light is stretched. The interval between wave crests gets longer. The light appears redder. The faster it's moving, the redder the light. If a galaxy is moving closer, the light is compressed and appears bluer.
After many years, Hubble could sit down and look at this great quantity of information, and he plotted a chart. He plotted for the nebulae the motions against the distances, and he found something truly amazing, a straight line.
He found that the distance of a galaxy is proportional to its velocity. So as you go twice as far out, turns out the velocity is twice as big. You go 3 times as far out, the velocity is 3 times as big. We live in a world, I mean, a big world, and a universe where everything's rushing apart, and it's happening in a way we call Hubble's law, where the velocity is proportional to the distance.
An expanding universe. How could that be when the whole history of human thought assumed, just took for granted, that the universe is this fixed thing, and how could it change? The universe is everything. How could it have an evolutionary path? Because if you had an expanding universe, that might mean it had a beginning. It might mean it'll end. This is a discovery for the ages.
Before Edwin Hubble's discovery, even the great physicist Albert Einstein assumed that the universe is fixed and eternal. His original equations for general relativity had predicted a changing cosmos, but Einstein was unable to believe his own theory. So he added what he called a cosmological constant to bring the universe to rest. Years later, in 1931, Einstein travels to Mount Wilson to meet Hubble. While there, Einstein declares that his cosmological constant is the greatest blunder of his scientific career. Of course, by this time, Einstein can afford to admit to a mistake or two. He's already renowned as one of history's greatest scientists, the man who redefines gravity, space, and even time. At the age of 22, at the turn of the century, Albert Einstein is living in Zurich and facing an uncertain future. He dreams of becoming a professor of physics, but he can't get a job. He has alienated most of his college teachers, and they won't give him the recommendations he needs. In early 1902, he moves to Bern. He's tired of scraping by with what he can earn giving private lessons, and a friend's father has offered to help him get a job there. It's with the Swiss Patent Office. He's a technical clerk, third class, reviewing applications for patents on new inventions.
Einstein was a perfect fit for his patent work. And those patents that he considered were, in my view, absolutely formative of his scientific style. He'd sit down every day with stacks of documents, and his job was to strip away all the complications, to take a patent like this and figure out, did this violate the basic laws of physics? What was its central idea? Was it that central idea new, or was it something that had been known? And those sorts of decisions, which he made every day, looking at these new devices, shaped his sense of how to strip down a physical problem down to its absolute essentials. What are the principles?
It's this same approach that compels Einstein to re-examine fundamental assumptions of classical physics, including ideas about space and time that seem to everyone else inescapable. In the early 20th century, everyone, from physicists to sports fans, takes for granted that a mile is a mile, no matter where the race is run. That the runner who finishes in 4.5 minutes is faster than the one who finishes in 5. Common sense tells us that time and space are the same everywhere and for everyone. Indeed, that was Isaac Newton's starting point when he wrote down his laws of motion and gravity in the 17th century. Laws that seem to explain everything from the flight of an arrow to the orbits of planets. But Einstein is willing, where others are not, to question everything, even our common sense view of the universe.
All I have tried to do in my life is ask a few questions. Could God have created the universe any other way, or had he no choice? And how would I have made the universe if I had the chance?
Einstein is driven to ask such questions by a problem he sees with the traditional description of light.
He knew from Maxwell's equations, from the great classical physics that had preceded him, that light could be understood as a wave, and that every time you saw a wave of light, it was always traveling by you at some enormously fast speed, like 186,000 miles a second. So we were always in the position of somebody, say, standing on the beach, watching a train of waves go by. Now, with any kind of wave that you've ever seen, or Einstein had ever seen, you could always catch up with it if you went fast enough. If you had a bunch of waves going down a canal and you got on your horse and rode alongside it, you'd see the wave just frozen, as if it was not moving, because you'd be moving with it. And Einstein's thought to himself was this: what if I caught up to a light wave? What if I went as fast as light was going? Would I see it still the way the horseman sees the waves in the canal if he catches up to it? And then he thought to himself, well, that would be such a strange sight. It doesn't correspond to anything anyone's ever seen, a still wave of light.
Einstein is convinced that light wouldn't be light if you could catch up to it. But in classical physics, you can catch up to any wave, and light is a wave.
How could it be that there was a wave moving along that you couldn't catch up to? He didn't know how to solve the problem. He didn't even know how to articulate the problem fully, but there was something wrong.
Children who wonder about things like light, time, and space are satisfied with the stock answers and never give them another thought as adults. But because I was a late developer, I first pondered such simple questions as an adult, and so probed them more deeply and tenaciously than any child would do.
In order to simplify the problem he sees with light, Einstein uses a series of thought experiments that take place only in his imagination, like a journey on a train.
From James Clerk Maxwell's equations, we know that the light reflected from my face traveling toward this mirror must move at 186,000 miles per second. Okay, Einstein said, but what if the train were moving at the speed of light?
One possibility is the train catches up to the light waves, so they never reach the mirror. But Einstein is convinced this can't happen. Light can't stand still.
And what does it mean if I do see my reflection in the mirror? Well, from my point of view, everything is just fine. But for the person standing outside of the train, there's a problem. That person sees the train moving by at 186,000 miles per second, and therefore the light reflected from my face traveling toward the mirror must be traveling at twice that rate, or 372,000 miles per second.
372,000 miles per second is the speed of light added to the speed of the train carrying the light. Physicists have added speeds this way since the days of Galileo. But Einstein concludes this simple adding of velocities is wrong, because the speed of light never changes. It's always 186,000 miles per second, even if its source is in motion. Whether on or off the train, you have to get the same measurement for the speed of light. The stunning consequence of this is that someone off the train measures rulers on the train as short and clocks on the train as running slow.
In a flash of brilliance, Einstein proposes that distance and time are not absolute, that a foot and a second measured on the train are not the same as a foot and a second measured off. Distance and time are relative.
Hold on. We're taking off.
Fortunately, this phenomenon is only noticeable close to the speed of light. Imagine yourself alongside early 20th century science fiction swashbuckler Flash Gordon. When not fighting the bad guys or trying to escape from some monster, you're dashing around the galaxy at incredible speeds. While you are, your clock and those back on Earth are running at different speeds. Assuming you've been gone for the better part of a year, when you get back, everyone you knew will have been dead thousands of years. It's the ultimate example of relative time. But Einstein isn't finished quite yet. He still has to conjure up the most famous equation of the century, E equals mc squared.
Einstein realized that not only does time slow down the faster you go, he also realized that when objects move, they get heavier as they move. It was a curiosity. Why should objects get heavier as they move? And then he suddenly realized that the reason why objects get heavier as they move is because the energy of motion is being converted into mass. Now think about that for a moment. The energy of motion is being converted into mass. This means that energy is turning into mass, and mass is turning into energy. And Einstein quickly wrote down, it's only one step, quickly wrote down the equation that relates energy to matter, and it is exactly E equals mc squared.
Einstein's theory of space and time is called special relativity. Physicists are intrigued, but little changes in Einstein's life. With a growing family to support, he remains at the patent office and moves on to another, even greater intellectual challenge. Special relativity applies to objects moving at constant speed, but most movement involves acceleration, speeding up or slowing down. So Einstein sets out to extend relativity to cover accelerated motion. It turns out to be one of the hardest problems any scientist has ever taken on. Einstein struggles with it for 10 years.
Now, most of us physicists, when we grapple with a problem that we can't understand, we give up and say, God is malicious. He's a nasty God. He's giving us problems that no human can understand. Einstein didn't have that philosophy at all. He didn't say that God was malicious, teasing humans with problems that were beyond human ken. He said God is subtle, that only if we dare to penetrate into the essence of things, then we would find the answer.
To get to the essence of accelerated motion, Einstein once again turns to a thought experiment.
Imagine this elevator were located in deep space and uniformly accelerating upward. With no windows and no connection to the outside world, Einstein said it would be impossible for us to determine whether or not we're moving. But you might say, I feel the pressure on my feet. But his response to that would be, but how do you determine whether that pressure is caused by the elevator moving upward through space with uniform acceleration, or by the elevator simply sitting on the surface of the Earth and you're feeling the effects of gravity?
The fact that you can't tell the difference, says Einstein, means acceleration and gravity must somehow be the same. He concludes, after a series of incredibly complex calculations, that this is only possible if space and time are curved. According to Einstein's theory of general relativity, the curvature of space is caused by the presence of massive objects. Newton had it right that a body in motion tends to stay in motion in a straight line, the shortest distance between 2 points. But in curved space, the shortest distance between 2 points is a curved line. An object experiences acceleration around the curve as gravity. The Earth orbits the Sun not because of a mysterious force, but because the Sun curves the space around it. The Earth is simply traveling the shortest path through curved space. Einstein's theory of general relativity perfectly describes the motions of planets, stars, and galaxies, both in space and in time.
Suddenly, physics could say something about the fate of the universe. It could ask questions about whether the universe as a whole had a certain curvature, whether it would come back in on itself, whether it would expand out forever. General relativity had a scope as infinite as the universe.
The world is not the same place once you understand these theories. Space and time are somehow the same thing. That's very different from my experience as I go through life. And I can never go back to looking at things the way they were before I understood this theory.
In 1921, Albert Einstein is awarded the Nobel Prize for Physics. But it isn't for his work on relativity. Apparently, that's too weird for the awards committee to accept. Instead, Einstein is honored for other contributions, including a paper on the nature of light. This paper ultimately leads to a second revolution in physics, only this time it's too weird for Einstein himself to accept. It's called quantum mechanics. Quantum mechanics comes out of the struggle to understand the structure of atoms. What physicists in the early 20th century learn is that in the world of the very small, the seemingly impossible is commonplace. Things don't exist until someone looks at them. We're unable to say exactly what path something takes to get from point A to point B. Uncertainty and chance are woven into the very fabric of existence. One of the key figures in the quantum revolution is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. Only the screams of an ardent fan snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that the budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms. Atoms had been seen as amorphous blobs of positive charge studded throughout with negative electrons. In fact, Rutherford says, they're more like little planetary systems. All the positive charge and virtually all the mass is concentrated in a tiny nucleus, around which the electrons orbit like planets around the sun. This is the courtyard at Cambridge University, where Rutherford began and ended his scientific career. Imagine an atom this size.
If we think of that being the size of an atom, then the size of the nucleus would only be 1 millimeter in diameter. That's a bit smaller than this little grain of sand that I've got in my hand here. In other words, what it means is atoms are essentially empty space.
Now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy, because if it's mostly empty space, they should pass right through one another. Well, what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields.
When the electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now, this means that I'm not really sitting in this chair at all. The atoms of my body are about 1 angstrom hovering over the atoms of this chair.
Rutherford's conception of the atom is a breakthrough, but almost immediately he finds a paradox at the heart of it.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very secure prediction of classical physics. And that's catastrophic. What it's telling you is that atoms cannot exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom. But Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. Would have a different orbit, would be stable, would have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
Bohr's idea that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
This is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake. In 1926, Werner Heisenberg, a 25-year-old German physicist, comes up with a mathematical description of atoms that goes a long way toward legitimizing Bohr's view. Classical physicists remain unconvinced. Heisenberg's mathematical matrices are too complex, and the mysterious comings and goings of electrons are just too hard to imagine. Within a year, an Austrian named Erwin Schrödinger offers an alternative.
Schrödinger had this beautiful theory of the electron as a wave. It was smeared out over space and time. It wasn't a particle at all. Physicists loved this idea. We had a physical picture. We could look inside the atom. Physicists knew how to calculate with waves. They calculated waves as an undergraduate in college. They knew how waves went around and formed orbits. So the appeal of the Schrödinger picture was that it was pictorial. It was almost Newtonian. It was continuous. None of this quantum business. And you could calculate with it.
So which is it? Is matter made up of waves or particles? They seem to be complete opposites. Waves can pass through one another, sometimes canceling each other, sometimes making even bigger waves. But particles, on the other hand, bounce, smash, exert force when they meet. They can't cancel each other out.
So these two pictures clashed with each other, and they debated. And they had arguments, and they yelled and screamed at each other. In fact, one day, Heisenberg was so worried that he simply came down with hives and hay fever and tremendous case of allergies, worrying about whether or not the rival picture was correct.
In 1926, Bohr and Heisenberg invite Schrödinger to Bohr's new institute in Copenhagen to try and work out their differences. Heisenberg writes about the visit.
Though Bohr was an unusually considerate and obliging person, he was able in such a discussion to insist fanatically and with almost terrifying relentlessness on complete clarity in all arguments. He would not give up, even after hours of struggling, until Schrödinger had admitted that his interpretation was insufficient. Every attempt from Schrödinger's side to get around this bitter result was slowly refuted, point by point, in infinitely laborious discussions.
Bohr's wife nurses Schrödinger when he falls ill from exhaustion. She brings him tea and cake, even as her husband sits on the edge of the bed continuing the argument. Still, Schrödinger clings to his classical view, wearily noting at one point, if one has to go on with these damn quantum jumps, and I'm sorry I ever started to work on atomic theory.
The essence of the Bohr-Heisenberg picture was that the electron was a particle. However, there was a certain amount of uncertainty with regards to where the particle was. Now, one day, Heisenberg was so paralyzed, worrying about all these problems, that he took a walk in the park. Outside his institute, there's a famous park, and late at night, he walked through the park wondering, how can it be? How can it be that you don't quite know where the electron is? And then in a flash, he understood. Because to understand where an electron is, you have to look at it. To look at it, you have to shine a light on it. But when you shine a light on it, that disturbs where the electron is. So the very fact of observing an object changes its location. Therefore, he realized that uncertainty is an essential part of his picture.
Heisenberg calls his insight the uncertainty principle. In a clear mathematical way, it says the more you know about a particle's position, the less you can know about its speed and direction. And the opposite is also true. The more you know about a particle's speed and direction, the less you can know about where it is at any given time.
And when he finally had that idea, he realized that he could merge the Schrödinger picture with the Bohr-Heisenberg picture to give us the modern-day theory of the quantum principle. In other words, the electron is a point particle, but you don't know quite where it is. And the probability of finding it at any given point is given by a wave, the Schrödinger wave. So we now have this beautiful synthesis of waves and particles.
Heisenberg's principle indeed is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here. And I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall or screen, projection screen, and what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
According to the quantum theory, even the most bizarre events have a probability of taking place. There's a certain probability that I will dissolve and simply rematerialize on the other side of that brick wall. Now you may say to yourself, well, that's impossible. We've never seen anyone dissolve and rematerialize on the other side of brick walls. But we actually give this problem to our graduate students. To our PhD candidates, we ask them to calculate, using the quantum theory, what is the probability that you will find yourself on the other side of a brick wall? Now, to tell you the truth, you would have to wait longer than the lifetime of the universe for such an event to take place. So you don't have to worry. Your atoms are not going to dissolve, and you're not going to rematerialize on the other side of brick walls. But there is a probability you can calculate for that event happening.
And then you can ask yourself the question, do I understand it? I don't even know what that means, understanding. I have problems with that. Physics describes things, describes phenomena. And as long as it is predictable, as long as that formalism applied in a certain situation gives you the right answer, who cares? Who cares what the meaning is of understanding? I think I leave that up to philosophers. And I think they don't have a clue either, of course, but they... Yeah.
There are some physicists who refuse to accept that quantum mechanics represents the full story of the subatomic world. The most famous is Albert Einstein.
Quantum mechanics is very worthy of regard, but an inner voice tells me that this is not the true Jacob. The theory yields a lot, but it hardly brings us any closer to the secret of the old one. In any case, I am convinced that he doesn't throw dice.
He couldn't believe that there were big patches of the world about which we could not know. And his idea, from early on in his life, all the way to the end of his life, was that there ought to be a set of equations, deterministic, causal, ordered, formulated in such a way that they could tell us everything about a future in terms of everything about the present. And quantum mechanics wouldn't allow it. He couldn't stand that idea.
The world's greatest physicists gather in Brussels in 1927. Einstein challenges Bohr and the idea that uncertainty rules the world. Werner Heisenberg writes in his diary,
"We all stayed at the same hotel. The discussion usually started at breakfast, with Einstein serving us up an imaginary experiment by which he thought he had definitely refuted the uncertainty principle. In the course of the day, we would have discussions on the matter, and as a rule, by supper time, we would have reached the point where Niels Bohr could prove to Einstein that even his latest experiment failed to shake the uncertainty principle. Einstein would look a bit worried, but by next morning he was ready with a new imaginary experiment more complicated than the last."
One of Einstein's challenges is so clever, it has Bohr deeply concerned for the future of quantum mechanics. Physicist Leon Rosenfeld writes,
Bohr did not see the solution. I shall never forget the sight of the two antagonists leaving the hall. Einstein, a tall, majestic figure, walking quietly, with a somewhat ironic smile, and Bohr trotting near him, very excited. During the whole evening, Bohr was extremely unhappy, going from one scientist to another, trying to persuade them that it couldn't be true, that it would be the end of physics if Einstein were right.
Bohr spends a sleepless night in his hotel room before he discovers a flaw in Einstein's argument. Ironically, it involves a subtle application of Einstein's own theory of relativity.
Bohr and Einstein are an astonishing pair. In many ways, they loved each other. They loved talking to each other. They loved engaging with each other's ideas. And yet they wanted such utterly different things from physics that they never really could see eye to eye.
God does not throw dice was Einstein's unshakable principle, one that he would not allow anybody to challenge. To which Bohr could only counter, nor is it our business to prescribe to God how he should run the world. Einstein and Bohr had their last battle about quantum mechanics in 1933. By this time, both relativity and quantum theory are almost universally accepted by physicists as the most powerful ideas they have for explaining the world. Now, attention shifts to another challenge, figuring out what goes on inside the atom. Physicists want to know what holds the nucleus together. They want to know if protons, electrons, and the newly discovered neutrons make up everything in the universe, or if these particles are made up of something even more fundamental. In the process, what begins as an intellectual quest turns out to have explosive consequences. In the early 1930s, Albert Einstein emigrates to America to escape the rising tide of fascism and anti-Semitism in Germany. Before the decade ends, many of Europe's finest scientists are forced to make the same journey. Among the last to leave is Niels Bohr. He arrives in the United States in 1939, bringing with him stunning news. In Hitler's Germany, two scientists have split an atom of uranium, releasing in that moment some of the tremendous energy bound up in matter. Using simple equipment widely available, they produced the first evidence from a controlled experiment of Einstein's famous equation, E = mc².